Hi everyone. I am Haosen Lee from Nanyang Technological University. I am presenting the work learning to animate images from a few videos to portray delicate human actions. This is a joint work with Ingchen Yu, Qilong Wu, Han Wangzhang, Song Bai, and Boyong Li. While current video generation models are impressive, they are still far from perfect. State-of-the-art models such as Kling and Wan continue to struggle with physical authenticity and temporal stability when generating complex human actions. As shown in the example, when producing a person shooting a soccer ball, the models generate deformed limbs and failed interaction with the ball. This difficulty arises from two aspects. First, the complexity of the human skeletal and joint system requires precise coordination. Second, most video datasets are long-tailed and complex athletic actions are rare, making it hard for models to learn their underlying physical dynamics. To efficiently generate delicate human actions, we study a few-shot animation task using only 16 videos per action. The model takes a reference image and a caption as input, where the image defines the initial state, including the actor, environment layout, and human-object spatial relationship. This is especially useful for film and video production, where rare or newly designed actions must be animated from only a few examples. The main challenge is overfitting to appearance in limited data. To generalize motion across different characters and backgrounds, the model must disentangle motion from appearance and learn generalizable motion patterns. To learn generalizable motion, we propose Flash. The key idea is, we require the model to reconstruct two videos that share the same motion but have different appearances, using the same learned motion features. If the learned motion features are entangled with appearance or not transferable, reconstruction quality will degrade. High-quality reconstruction across different appearances forces the model to learn generalizable motion representations. Specifically, we first construct video pairs with identical motion but different appearances through frame-level strong augmentation using Gaussian blur and color jittering. Next, in the intermediate layers of the UNet, we align the motion features of the original and augmented videos. Within the temporal attention layers, we identify motion-related channels according to the variance across frames and transfer them from the original video to the augmented video. In the cross-frame attention layer, we treat the first frame as the key and value, and the subsequent frames as queries, so that the resulting attention scores capture inter-frame correspondences. We then transfer these correspondences from the original video to the augmented video. Together, these two steps ensure that both videos share the same motion features. Finally, we reconstruct both videos. If the motion representation is not transferable, reconstruction will be poor. By minimizing reconstruction loss, the model is encouraged to learn motion features that generalize beyond specific appearances. Beyond motion generalization, Flash also enhances transition smoothness between the user-provided reference image and the generated frames. To achieve this, we design a dual-branch architecture that extracts multi-scale features from the reference image and injects them into each decoding stage. The warping branch predicts feature displacements between the encoder features of the reference image and the decoder features of the generated frames, then transfers local details based on these displacements. The patch attention branch retrieves global details through cross-attention, where the decoder features of the generated frames serve as queries and the encoder features of the reference image serve as keys and values. By integrating both local and global details, the generated frames remain visually consistent and faithful to the reference image. Our quantitative results show that Flash clearly outperforms existing methods. It achieves a 66% user preference rate. Flash also delivers state-of-the-art performance on cosine RGB, cosine flow, temporal consistency, and CDFVD, demonstrating superior visual quality and motion consistency. Our qualitative results further demonstrate that Flash outperforms both commercial AI video generators and existing image animation methods. The examples show strong physical realism and stable motion dynamics of the generated videos. A key advantage of Flash is its robust generalization. It successfully animates diverse inputs, including real-world internet images and AI-generated contents. As shown in the examples, it generalizes to non-human characters, preserving motion structure and consistency across a wide range of visual styles and subjects. For more details and additional generated videos, please refer to our paper and project page. Thank you.